we're going to take a look at symmetry today. You maybe talked about symmetry in a previous math class. And the type of symmetry you talked about was line symmetry. And if you recall, when figures have line symmetry, they can be folded so that they have matched. So line symmetry is where you draw a line through a figure, and you fold the figure on that line in half. Everything will match up perfectly. Okay? So to review, we take a look at this first one. Determine first if there is line symmetry, and if there is, draw them in and state how many lines you drew. So we take a look at that first figure. What's one line of symmetry we can draw? Down the middle. Yeah, we fold it. All the sides are the same, so we cut it right down the middle. And that's up. Where else? Good. Do the same thing, but on this other vertice. Go from the corner to the side, and what's the other one you can draw? Corner to the other side. Are there any other lines we can draw? Nope. I don't see any. Can't go this way. That doesn't match up. So that's about all we can draw. How many lines did we draw? 3. Okay, sometimes what happens, we draw our lines, and then we go 1, 2, 3, 4, 5, 6. We count the ends. Well, you're double counting lines. When you count this, and then you're counting the same line twice. So you just kind of keep track as you go how many lines you drew. Okay. We take a look at the next figure. Where can we draw a line of symmetry? Right down the middle again. Where can we draw another line of symmetry? Okay, yeah. To do the same thing, go from point, corner to side, corner to side, corner to the side, corner to the side. A little off. How many lines of symmetry did we draw? 5 lines of symmetry. Again, if you were to take that figure and fold it along that line, it will match up perfectly. Okay? All 5 of those lines. If we take a look at C, where can we draw a line of symmetry for C? Right down the middle. Are there any other lines of symmetry we can draw? Nope, that is the only one. So it only has one line of symmetry. Okay, one thing to take note. In this triangle, all the sides and angles are the same. How many sides does the triangle have? Oh boy. How many sides does the triangle have? 3. How many lines of symmetry did it have? 3. This one, all the sides and angles were the same. How many sides did this have? How many lines of symmetry did it have? 5. This didn't really have any sides or angles or anything, so it didn't really match. Okay? That's a helpful hint. Okay? We call these figures regular figures. Regular figures, all the sides and angles are the same. So when that happens, the line of symmetry will match however many sides there are. If it's not a regular figure, then it's not going to match. Okay, different. Okay? Questions over that. It's a little shortcut. You still have to draw them in, but at least gives you an idea of how many you're drawing. So in the coordinate plane, lines of symmetry are called lines of reflection. That's because if you reflect a figure over its line of symmetry in the coordinate plane, the figure will map up onto itself. So when the directions ask you, determine the transformations that will map a figure onto itself, all you're doing is trying to find lines of symmetry for that figure. Okay? That's exactly what we did in example 1. It's what we're going to do in example 2. The only difference is it's in the coordinate plane, but it still has lines of symmetry. So we take a look at example 2. We have a regular hexagon and it's centered at the origin. Determine which of the following transformations would map the figure onto itself. I see the words map a figure onto itself. That's telling me in my head I'm looking for symmetry. Looking for lines of symmetry. So you're just going to go down your list and draw all these lines in. And ask yourself, is that a line of symmetry? If it is, it's an If it's not a line of symmetry, it's not an answer because it won't reflect onto itself if it's not a line of symmetry. So if we take a look at A says a reflection over the x-axis. So I'm going to highlight the x-axis. Is that a line of symmetry for the figure? Yeah, that's your answer. Because if we reflect, and if you're unsure, you're looking at that line, I think it's a line of symmetry, but I don't know. Just do the reflection. Reflect the figure. Take a point. I'm going to reflect this corner over the x-axis. 1, 2, 1, 2. It mapped up with another corner. I'm going to check another one just to be sure. 1, 2, 1, 2. That mapped up with another corner. And then if I 1, 2, what? That mapped up. 1, 2. The corners are matching up with other corners. So that means it's mapping up onto itself. Okay, so that is a line of reflection. It's a line of symmetry. It's an answer. If we reflect this figure over that line, we flip it, it's going to look exactly the same. It mapped up onto itself. B says a reflection over the line y equals x. So I'm going to graph that line. When we graph y equals x, where do we start at? We graph y. Where do we start? 0, 0, 0, the origin. And then we just go up 1 over 1. And connect. When we connect, ask yourself, is that a line of symmetry? If I could fold that figure over that line, will it map up? No, it's not going right, and you can tell it's not going right down the middle. Because this side, on this half of the line, it's just an itty bitty bit. There's not a lot there. On this half of the line, it's a lot longer. So it's not cutting anything in half. So if we fold it, it's not going to map up. Again, visually, if you look at that and you're like, I don't know if that's a line of symmetry or not, just do the reflection. Okay? I'm going to start with this corner piece. I'm going to reflect it over that line. 1, 2, 1, 2. Did this corner map up with another corner? No, it landed in the middle of the side, right? So that didn't, a corner has to land on another corner. It didn't, not a line of reflection. Not going to be an answer. It's not going to map up onto itself. Corner has to map up with another corner for it to work. Well, if y equals positive x works, do you think y equals negative x is going to work? No, because it's the same exact line, it's just going in the other direction. It's just going this way. And we already decided that's not a line of symmetry. Okay. If we take a look at D, D is saying a reflection over the y-axis. So when I highlight the y-axis, ask yourself, is that a line of symmetry? Yeah, that's an answer. If we flip that line, that figure over that line, it will map up onto itself. And it's a line of symmetry. And again, if you're unsure, just do the reflection. I'm going to do this one. I'm going to count 1, 2, 1, 2. Did a corner land on another corner? Yeah. I'm going to try another one just to be sure. 1, 1. Did a corner land on another corner? One more to be sure. 1, 1. Yep. The corners are landing on opposite corners, so it's going to map up onto itself. And then lastly, E, it says a reflection over the line y equals negative 1. I'm going to graph that line. Go to where y is negative 1. What kind of line are we going to draw through that? Horizontal or vertical? Oh, no. So ask yourself, is that a line of symmetry of the figure? Nope. So when we flip it, it's not going to land on itself. Okay? Even just do one. I'm going to try this one. 1, 2, 3. 1, 2. No, it landed down there. Did not map onto itself. The corner did not map onto a corner. So those are the only two lines of symmetry, or lines of reflection, If we were to flip that figure over those lines, it will map up onto itself. It would stay the same. Questions over that? At the bottom, there's another type of symmetry that you maybe have not heard of before. That's called rotational symmetry. And what rotational symmetry is when you can rotate a figure less than 360 degrees about its center, and it will map up onto itself. Okay? The order is the number of rotations that occur to create rotational symmetry. There's really no order of one, since any figure without rotational symmetry has an order of one. Okay? So, this is not a true equilateral triangle. They said it was. It's not. They lied. Because when I do rotational symmetry, it doesn't work how I want it to. I need to find a new equilateral triangle. But we're going to determine if the following figures have rotational symmetry. Yes, you determine the order and angle of rotation. And the angle of rotation is just how many degrees you're rotating it so that it maps up onto itself. Okay? So I'm going to highlight this. Trace the figure. Okay? And then I'm going to actually turn it. And it's not a true equilateral triangle because it doesn't work how it's supposed to. But I'm going to rotate it. Rotating, 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 rotating. If it was a true equilateral triangle, it would look like that. So I wrote, there's one rotation where it mapped up onto itself. Rotate it, rotate it, rotate it, rotate it. And if it was true equilateral triangle, it would look like this. There's two rotations where it mapped up onto itself. And then rotate and rotate and rotate. And I'm back to the beginning. How many rotations did it map up onto itself? We need a full circle. 3. We did 3 rotations. 1, mapped up. 2, supposed to map up. 3. 3 rotations. Okay? So that's the order. That's how many times we rotated it. We had to figure out the angle of rotation. How many degrees did we rotate it to get it to map up onto itself? To do that, what's a full circle? How many degrees are in a full circle? You do 360 divided by however many times you rotated it. What's 360 divided by 3? 120. So each of those rotations, this first one, that was 120 degrees. The second one was another 120 degrees. The last one was another 120 degrees. All 3 of those rotations were 120 degree rotations. Questions over that? We take a look at B. I'm going to trace this guy again. And again, you can't magically trace your figures, but rotating your paper might help. Okay. Well, let's rotate it. And it's not going to map up perfectly because I didn't trace it perfectly. But it'll be pretty close. We're going to see how many times we can rotate it. There's 1, 2, my tracing was perfect to be right on. 3, 4, 5. We could rotate it 5 times in a full circle and it mapped up onto itself. So the order is going to be 5. How do we find the angle of rotation? 360 divided by 5. And what is 360 divided by 5? 72. Okay. So each rotation, that was 72 degrees. This was another 72 degrees. That was another 72. Another 72. Another 72. So you're doing a bunch of 72 degree rotations. And this last one, this part. Is there any way we can rotate this circle? No. Or this heart? We we do a full circle and it never mapped up onto itself. It took one full rotation to map up onto itself. And when that happens, when it has an order of 1, there's no rotational symmetry. We saw from the other one it had line symmetry, but there's no rotational symmetry. Think if the angle of rotation ends up being 360 degrees, there's no rotational symmetry. The angle of rotation has to be less than 360 degrees. Okay. Questions over that? So now we can apply it to the coordinate plane. I use the same figure from the front. We have the same regular hexagon. Right? Graph of the coordinate plane. And now we know a new type of symmetry. So the same rules still apply. Whether it's in the coordinate plane, whether it's not in the coordinate plane. Okay? When asked to determine the transformations will map up onto itself, you're looking for line symmetry and you're looking for rotational symmetry. You can look for both. Okay? So same problem as the front, which is mixed with line symmetry and rotational symmetry. So if we look, go down our list. A is a reflection over the x-axis. What did we say about that? Was that a line of symmetry? Yeah, so it's going to map up onto itself if we reflect over that line. Did we say y equals x was a line of symmetry? No, we did that on the front, and we said it was not a line of symmetry. Here's a new one. This is a rotation of 60 degrees about the center of the figure. Okay. Well, to figure out if that works, because we never talked about any kind of rule on how to do a 60-degree rotation. Okay. But all you have to do is figure out, well, what's my angle of rotation? Do what we did on the front. Do 360 divided by, and I forgot to talk about one thing, I'm sorry. Let's go back, it'll help us with the order here. What did you notice about this equilateral triangle? How many sides does it have? What was the order? We have another regular figure, all the sides and angles are the same. How many sides did it have? What was the order? Okay. Here we have a regular hexagon. How many sides does a hexagon have? So what do you think the order is going to be? 6. So when you have regular figures, the order is however many sides there are. Same with the line of symmetry. However many sides there are, that's how many lines of symmetry it will have. Or lines of reflection. Well, what's 360 divided by 6? That's its angle of rotation, meaning if I rotate it one time and it maps up onto itself, that was a 60-degree rotation. So would a 60-degree rotation about its center work? Yeah, that's its angle of rotation. That's going to be an answer. Okay. G says a reflection over the y-axis. I'm going to draw that in. Did we say that was a line of symmetry? Yeah. Circle that one. E says a rotation about the center of the figure, 90 degrees. Is that going to be an answer? No. Rotating at 90 degrees is not going to work. But what about 240 degrees? How does 240 work? Yeah. Perfect. 240 degrees. If you go back to the beginning. Just as Parker said, that's 4 60-degree rotations. There's one 60, another one makes 120, another one makes 180, another one, our fourth one, makes 240. So that does map onto itself. The reason why 90 didn't work, the angle of rotation doesn't go into 90 evenly. 90-degree rotation, this is what a 90-degree rotation would be. Oh, nope, that's not what I wanted. Go back to the beginning. This is a 90-degree rotation right there. Did not map onto itself. So these 4 transformations would map that figure onto itself. So the lines of symmetry, or it goes with the angle of rotation. Questions over that? Okay. We're going to say that last example